So 4.2 is about a thing called Extrema, which is the plural for the word extreme. So an extreme means you're either like really high or really low. Okay, so what we're going to do is use derivatives to figure out maximum values and minimum values of math functions. This doesn't really involve graphing per se, but a graph can be helpful to understand what's going on. So if we look at this graph of like wiggly stuff, this point right here is called the absolute max. Because of all the points on the graph, that's the highest that ever went. This point right here would be the absolute min. Because of all the points on the graph, that's the lowest that it ever goes. Would it be possible to ever have two absolute maxes?
Yes.
Yes. You could have two mountaintops that happen to be the exact same height of a mountaintop. Is that likely? Probably not, but it could happen. You could have a tie for absolute max. You could have a tie for absolute min. But most of the time, you'd get one max, one min in the absolute world. There's also a thing called a local max. This point right here would be called a local max. Because even though it's not bigger than everything in the whole problem, in this little area of the world, this is as high as it went in its own neighborhood. It's the big fish in the small pond, if you like that reference. This would be a local max. This right here would be a local min. Even though it's not an absolute min, because this went lower than it later in the graph, that's the lowest in its area. This would also be a local max. If you're an absolute max, you have to be a local max. And this absolute min would also be a local min. If you're an absolute min, you have to be a local min. Do you have a thought on something else on the graph that would be a local max or min? The starting point, and therefore also the end point. This would be a local min, because from the start it went up. If from the start it went down, it could have been a max instead. This would be a local max, because since you come to the finish line on an upswing, that's the highest it is in that zone. If you limp into the finish line on a downswing, you could get a local min at the end. But that's the idea of what we're looking for. Locals, there's probably a lot of them. The absolutes, there's probably one of each, but you can get some ties on the absolutes. But that's the concept. Does that make sense? So here's our process in terms of how does calculus help us to do this. So the first thing we're going to do is make a list of what's called critical points. Okay, critical points are points that possibly are going to be maxes or mins. Not every critical point always pans out. Sometimes some of these critical points will be a dead end. But if it is going to be a max or min, it has to be in our list of critical points. But just because it's in the list of critical points doesn't mean it's going to pan out. You understand? So here's what we want to always take under consideration are endpoints, the beginning and end, like we just had on that graph. We'd want to look for any points where the derivative is 0. All of those mountaintops and valleys are points where the derivative would be 0. And I don't want to walk back over there and make the camera move. Okay, but if we're going like this, that's a positive slope. If you're going like this, it's a negative slope. When we hit a mountaintop, for just a moment, that tangent line goes horizontal. That has 0 slope. So points where the derivative is 0, those may be in our list. Another thing we might want to consider are points where the derivative doesn't exist. Because like that's a thing that we talked about because of the corner, we couldn't do the derivative, but that would still be a max. You know, if we went like that, derivative doesn't exist, but that's still a min. So sometimes derivative non-existent, sometimes derivative being 0, sometimes the endpoints. Those are all things that are worth consideration for us to scope out. Here would be a dead end. If we looked at this point right here, briefly, that goes horizontal. That has a slope of 0. That has a derivative of 0. But that's nothing. That's like in the middle of the Jackrabbit roller coaster double dip at Kennywood. Even though it does go 0 slope for a minute, that would be an example of a thing that might dead end on us. But here's our process. First for absolutes. The absolute process is a little simpler. To do absolute mins or maxes, the first thing we're going to do is find our critical points, what we just discussed here, the endpoints, derivative being 0, derivative being impossible. We'll make a list of critical points for x's. We're going to evaluate those x's, plug them in to the original equation we should be given, and that should get us some y's. And then we're going to pick the highest y to be the max, we'll pick the lowest y to be the min. And that's going to be our process for doing absolute max min. Does that make sense? We'll put that into use. So slide over a column. First thing we're going to do on every problem is going to be to do the derivative, because it is the derivative chapter after all. So if I say y equals x to the 2/3, these are our endpoints. We have to stay between -2 and 3. But first move will be, let's do the derivative. So the derivative of x to the 2/3 would be
2/3 x to the -1/3.
2/3 x to the -1/3. For analysis purposes and plugging in purposes, you might want to write these both a different way. Remember how to write 2/3 power a different way?
Cube root of x squared.
It is the cube root of x squared. How about if I want to write this also with a rooty thing, what would I do about a -1/3 power?
Put the cube root of x on the bottom.
Cube root of x on the bottom is true. Okay, so what we're after here, here's my list of critical points. -2 is a critical point because it was the beginning. It's an endpoint. 3 is a critical point because that's an endpoint. That's an end. We need to analyze this derivative and figure out, is there any way to make this derivative equal to 0? Or are there any numbers that would make this derivative not possible to exist? Can you think of any numbers like that?
Any, or 0.
0. We're not allowed to have 0 on the bottom, so that would be our one additional critical point. A lot of the homework, when we get to the derivative part, might look like this. If we wanted to see what made that equal to 0, you'd have to factor x.
-3 minus, or +2.
Haha, trick you. If that were a plus, we'd get 3's and 2's. But since it's a minus and we're different, we'd have to subtract to the middle number.
+1 minus 6.
Yeah, +1 minus 6. And this would give us up a
-1.
-1. This would give us up a +6. So in a question like that, we'd have 4 critical points. We'd have the 2 endpoints, and we'd have a couple other numbers. One thing to check about your critical points is make sure that they're in bounds. Okay, we just got this 0 a second ago. This problem has to live between those two numbers. 0 does live between those two numbers. So 0 does get to play on our list. But if this had been the question, and we got -1, that does live in those boundaries, but a +6 is out of bounds. +6 would not have gotten to play anymore with us. We'd have to discard numbers around us. There are some in the homework where the algebra of it will give you numbers that they've made out of bounds. So that's good news. You throw them away. So we found our critical points for x. Now we need to plug those into the original thing to get some y's. So I'll do the 0 first because life is easier with zeros. 0 to any power is 0. For the 3 squared is 9. So I'd be doing the cube root of 9. And I'm not going to even do that out. -2 when it squares is 4. This would be the cube root of 4. Then we skim through the y's. The lowest y is the min. And the highest y is the max. And that, while it was in the running briefly, it lost the election. That's just a big nothing. Okay with that? Point of emphasis that people will get confused. I'm going to stroll slightly to the left. I don't know if I'll leave the screen here or not. The absolute world involves plugging into the original. So we'll do the derivative in every problem, but absolute min-max problems, we get that critical point list, whatever order they're in is fine. Then we're going to go get the y's from the original. The original equation is what makes our main decisions happen. Okay with that? So then here's some foundational facts that'll feed into local has a little bit harder process. I wouldn't say hard. This isn't like a top 10 difficulty lesson, but I'll say harder than that. The locals are going to be determined by slopes. Derivatives, synonym for slopes. So if the derivative is positive for certain parts of the graph, that means that your function is increasing. We've had that in the work always. Positive derivatives mean increasing. Negative derivatives would therefore mean decreasing. What we're going to have to do is look for transitions. If there's a change, that's what's going to create these local maxes and mins in a second. If we have something that has a positive slope, and then it's followed by something that has a negative slope, you just created a mountain by doing that. You found yourself a maximum point. That would be a local max. I wouldn't memorize that. You can memorize it, okay, but I keep using my hands all chapter, or just imagining my hands and think positive slope is up, negative slope is down. Did I create a mountain or a valley? I just created a mountain, and that's a max. If I went negative, then positive, I go down, then up, that's creating me a valley. That would be a local min. And again, you can memorize that, or you can keep looking it up in your notes, but I prefer to just use my hands. If I'm coming out of the left end, positive, so I'm at the left end and I'm going uphill. That very beginning point, if I come out of it with an uphill positive slope, that had to be a local min. But if I had come out of that with a negative downhill slope, that original point would have had to be a local max. Again, you can memorize that, you can keep looking it up in your notes, but realistically, I just kind of think about it or use my hand if I can't quite visualize it. Right end is just opposite. If we go positive into the right end, that would be a local max if we finish on an uphill slope. If we go negative, that would be a local min if we finished on a downhill slope. You with those concepts?
Yeah.
That's how we're going to decide whether we have a max or a min, is based on whether it's increasing or decreasing and when it transitions and where it is. There's not going to, it'll take a little more thinking. Didn't take much thinking on these to go, oh, max is the highest, min's the lowest. Okay. But what we need is a change between increases and decreases, positives and negatives to do these locals. So here's my local strategy. We're going to find those critical points again for all the x's, but this time we're going to put them in ascending order, meaning from littlest to biggest, meaning number line order. So here we found those critical points and we just slopped them down in whatever order we slopped them down in. It didn't matter. Okay? But for these, I'm going to write them in number line order. Then instead of plugging in the numbers we found, we're going to have to use our imaginations and come up with new numbers that are in the gaps in between the numbers. And I'll explain that better when I have numbers to actually look at. We're going to evaluate not the original, but this time for our locals, we're going to plug into the derivative. And what we're not trying to do is get numbers. We're just trying to get positives or negatives, increases or decreases. Then from these increase-decrease rules we just discussed, that's how we'll decide on our maxes and mins. And then maybe at the end, if they want them, maybe we'll go get the y's from the original, but they don't even care about us getting the y's all the time. Sometimes we just don't even bother with that. It probably won't make total sense until we do one. Do you have a question about that at all before I slide away? So we'll do one. I'll slide all the way back to the left while I grab my notes paper and do the sample problem, and then I should be able to just hang out here the rest of the time and I'll make you keep moving. here because I don't think we need this anymore. So I have y equals negative x cubed plus 12x plus 5 staying between negative 3 and 3. And away we go. So first move, as always, just do the derivative. So the derivative will be
Negative 3x squared plus 12.
agreed. We're always worried about that derivative equaling 0. You could solve this a couple of ways. One thing you could do is just like start doing your opposites like algebra 1, like subtract the 12 out of there. You could divide by negative 3. This could reveal that x is
Positive or negative.
positive 2 or negative 2. Check those are inbounds, so we're going to keep all those numbers. So we're going to go negative 3, negative 2, positive 2, positive 3. I'm going to write those across a line where we are in the order that they're in the number line. A better way to usually do this isn't that algebra strategy. Factoring is usually better, and you'll see why in a second. I would probably think it's better to pull off a negative 3 to leave x squared minus 4, and then factor to get this. It still gets us negative 2, it still gets us 2, we're still in bounds, we still have that same list. I brought both of the boundary numbers, I brought both of the solution numbers, but that's like step 1 from the cheat list over there. Find the critical points, put them in ascending order. You okay with that? Then we're going to have to imagine some numbers in the gaps. I don't need to pick anything that's less than negative 3, because negative 3 was the beginning of the problem. We don't care about anything that's under negative 3. But I need to imagine any number in between these. So negative 2.5, or negative 2.1, or negative 2.9. You can imagine any number in the gap between these numbers. And it's going to be easier to put it into this stuff to decide on positive, negative signs than it would be to go here. Because if you're imagining like negative 2.5, you probably don't want to take that and square it and multiply by negative 3 and add 12 and try to like estimate what that is. It's a lot easier to go into these factors. So if we're imagining negative 2.5, this piece would be negative. This piece would be negative if we brought in a negative 2.5. This piece is locked in as a negative. Negative times negative times negative, a triple negative is negative. That's a zone where we're decreasing. Does that make sense? I think it's easier to plug into factors than it is that. Then we pick a number in this gap. 0, 1, 1.9 if you want it, negative 1.9 if you want it. Any number you want to imagine in this gap will do. I'll go with 0 because 0 is my friend. So if I plug 0 in, that's a negative factor. That's a positive factor. That's locked in as a negative factor. 2 negative factors makes it positive. That's an increase. And since we had a change here, this is going to be something. That's either a max or a min. We can figure that out in a second. If this had been a decrease, that means that did nothing. It's worthless. But when things change, that's meaningful. Between 2 and 3, pick a number. 2.5, 2.8, 2 point whatever. That would be positive. That would be positive. That's locked in as a negative, so that's a decrease. And since that changed, that means that is also something again. And we just accomplished mission 2. We imagined new numbers in the gaps. We decided whether the derivative made that increase or decrease, and now it's time for us to make our picks. You okay? So if we start at the beginning and decrease, that's a max. Because my arm says so. If we decrease out of the beginning was a max. If we decrease, that increase. Down, that up, that was a valley, that's a min. If we increase, then decrease. Up, then down, that's a mountaintop, that's a max. And if we finish on a downturn, if we're decreasing into the finish line, where we finished would be a min. Okay with that? Then some questions they do, some questions they don't want us to get the y's from the original problem. And I'm going to just take a pass on that for now. But if I wanted to take -3 and plug it into that stuff, I could get a y if I were instructed to do so. This -2 plugged in, I could get a y if I needed it. You know, this 2 plugged in, I could get a y. This 3, I could plug it in, I could get a y. You know what, they're on my paper, so instead of like working to do it, I'll just tell you what they are. The 3 would get you a 14, the 2 would get you a 21, the -2 is an 11, this is a -4. The numbers themselves aren't very meaningful. Like, don't try to make sense out of the numbers. Like, -4 is small, but it was a max. Positive 14 is bigger than that, but it was a min. But they're local. It's just in its area. It just had to win its area. And -4 won its area compared to -11. I guess those make sense side by side. This is a max, this is a min, because this beat that. This loses to that, so that's a min, that's a max. Maybe that makes sense. But I wouldn't try to make too much sense out of the numbers, because they're not trying to win the overall race, they're just winning their little area. So a positive number lost its area, while a negative number won its area. Yeah, it can happen. It's just how it goes.
So we don't care about absolute?
You do not. No, they'll either do absolute or they'll do local. There's no question they'll do both. They'll start off with absolutes and then they'll work their way into locals. Is that okay? I have a note on here to potentially do 2, 8, and 28. So I guess I'll just go to the homework page and do what my notes tell me to do. 2 is probably something, 2 might even be a graph. Let's see what that is. So the homework's on 216. The syllabus knows what the numbers are. Okay, it starts off with all of 1 to 6, and that's, I guess, why I'm doing 2. (216) 1 to 6. They want us to look at the graphs and decide whether it has absolute maxes or mins, and then tell like where they are. So if I looked at number 2 on 216, I'll wait a sec while you get there.
Number 2?
Yeah, so if I'm looking at number 2, the directions want to know, does this have absolute maxes or mins? So I look, does it have a highest point? Yes, it has a max. The max would be C. And then I look for a lowest point. Does it have a lowest point? Yes, it does. The min would be B. That's what you're working from 1 to 6. Now it gets a little more complicated when there's holes in the graph, because holes in the graphs can't count. Okay, what you're looking for is it has to be like a smooth part of the graph or a filled in dot can be your answers. A hole in the graph can't be your answer. So if you needed your answer to be a hole in the graph, then you might say it doesn't have a max or doesn't have a min because the hole in the graph doesn't count. Is that okay, 1 to 6? Mm-hmm. Then we just start to do odds. From 7 down, we'll do odds. So I'll do 8 first. 8, they start off so easy, it almost like makes it hard. So sometimes the first couple freak people out because they're easier than what I did. I did that crazy Rudy one was our absolute. So for 8, they give you this. The first step is to do the derivative. The derivative would be -1. The goal is that the derivative equals 0. That derivative can never equal 0 because it's locked in on -1. There's nothing for us to even do for it. So that derivative is useless. The only thing that we can do for critical points is use -4 and use 1. For the absolutes, once we get those critical points, you can put them in any order you want. The order doesn't matter. We just need to plug those into the original and get some lines. So -4 into this gets me 0. A 1 into this gets me -5. This is lower, -5 is lower, so that's the absolute min. 0 is higher, so that's the absolute max. And that wasn't much of a contest. The derivative was sort of stupid. As you work through the homework, the derivatives will start to have x's in them, and then you'll get one additional number. Or the derivative might have an x squared. Then you factor, maybe you get 2 more numbers. Maybe they even have x cubes in the derivatives. Now you factor it into the 3 pieces. Now there's 3 additional numbers. There becomes more of a contest, but the endpoints always are in the list, and anything the derivative gets you, as long as it's in bounds, is in the list. But there are, again, a couple in the homework that will go out of bounds, and those are garbage. From 8 to 26, or 7 to 26, the even ones, or the odd ones that we're doing, it's that strategy. But I have you skipping 17, because I don't feel like doing trig, 19, because I don't feel like doing trig, 21, because we don't know how to do derivatives of absolute values. We've never had that come up in the book, and now all of a sudden they're doing derivatives of absolute values. I don't know where that even came from on 21, so we're just going to take a pass on that. You feel okay up to 26?
I have one question for number 3. Since it's a corner, does that screw up?
No, corner, you can't do the derivative, but points where you can't do the derivative are in play.
Okay.
Yeah.
So the only things that you can't do are the continuity, discontinuity.
Yeah, discontinuities, you can't use them.
Okay.
Yep. So you're good, maybe up to 26?
Alright, and then for that section, if you have on the bottom a square root of an x, can every negative
Don't worry about negatives, because the whole graph would cease to even exist. Because that would be too many points to even check. There would be an infinite amount of negatives that are bad news. You only worry about 0 on the bottom, worry about that. But rooting negatives, don't worry about those. That's a good question. 28, they're going to do a local thing, but they've done some of the work for you. Okay, so on the one that I erased, there was a point right about here, and I can still see the remnants of it. There was a point where we had that derivative factor. And what they're doing for you on 27 to 34's group, they already did the derivative. They already factored it for you. They're stepping you in about halfway through the problem already on 27 to 34 because the derivative has been already accomplished. So they did the derivative on 28. They factored the derivative on 28. And they're ready for you to just roll. Okay. What they didn't do on this group is give you the endpoints. So you don't have endpoints. You just don't worry about it. There is no inbounds or out of bounds. Everything is inbounds. It's boundless. So from 27 to the end, they stopped giving you the stuff like this that establish the boundaries. In a way that makes your life easier. You lost a couple numbers you don't have to worry about, and it took away the idea of being out of bounds. So they did the derivative, they did the factoring. We've got to figure out what could make these 0. What makes this 0 would be 1. What makes this 0 would be -2. And if I do this, I'm already wrong. I've already wrecked myself. Why have I wrecked myself already? Check the details on step 1.
If you do the derivative is 0.
No, we're okay. Those are the right critical points. But note 1 is find the critical points and make sure that they're in ascending order. Because we're doing this we're thinking about numbers in the gaps on the number line, and if we write them all out of order, we're ruined before we even start. So 1 is first, but it's bigger, so go on the right. 2 came from the other factor, but it's smaller, so we'll put it first. Then we need to do imagination numbers. So this time we do need to imagine something smaller than -2, because there's no boundary. This is boundless. So imagine anything smaller than -2, like -100. If you put -100 into these, they're both going to be negative, and negative times negative is positive. So that's an increase. Then pick anything between these numbers. 0, If you put 0 in for these,
One's negative, one's positive.
one of each, so that's negative, so that's a decrease. Then pick anything bigger than 1, and sometimes I like to just go weird and think like a million, you know, because literally any number bigger than 1 works, but if you think of something crazy, sometimes you don't even have to think about it. You know, if we're thinking about what would happen if we put in a million, well, those are both positives, so that's an increased part of the world. Increase then decrease, max or min, that is a max. And decrease then increase by symmetry must be a min. You can't get the y's on this. Last time I finished this by going and getting the y's. This I can't, because to get the y's, I'd have to plug into the original problem, and they never gave me an original problem. They already gave me a halfway completed problem where they did the derivative and they factored. So this group from 27 to 34, that's our answer. And I'm fine just writing them like this. Like this is the way all of my answer keys look is, the way I lined this up is communicating that this number is a max number, that this number is a min number, that we're increasing beyond it, decreasing between the numbers, increasing before we get there. I'm fine writing the answers that way. I understand what you mean.
How come we're not doing the endpoints even?
We're not doing, there weren't endpoints.
Oh, okay.
So they stopped giving us the endpoints on number 27. There's no more endpoints till the end.
Okay.
35, they changed the game to make it a touch longer. 35, they are giving you the original thing. You'll have to do the derivative yourself. You'll have to factor it yourself, and then you'd repeat the process that we did. But starting on 35 to the end, since they are giving you an original, you can get the y's, and they will want you to get them. The directions on 35 start off, it says, the final phrase is, say where they are assumed, which is the x number we just got, but also what their values are. That's the y's that I can't get on number 28. But on number 35, to the end, you can get the y's because they gave you an original problem. Does that make sense?
You said you.
On 27 to 34, we can't get the y's because they didn't give you an original y equation. On 35 to 46, you can get the y's because they did give you an original y equation that you can plug these numbers in to the original equation and get the y's.
Are we doing the y's from 7 to 26?
7 to 26, you have to do the y's because the y's are what you use to make your judgment. So you have those x's, you plug on the absolutes, you get the x's, you plug the exact x's as they are into the original, that gets you y's, and you pick highest lowest. The local is completely different because you get these numbers and you don't put them anywhere. You just use these numbers to help your imagination imagine the right sized number. They don't plug into the original the way the absolute did. They plug into the derivative. You don't care what you get in terms of a number, you only care what you get in terms of a sign. And then you've got to think your way through the max min. Max min is more of a process. The absolute, locals I should say, is more of a process. The absolute is a pretty quick pick. Get the X list, plug them in, get Y list, boom, you're out. These you've got to imagine things and think about signs and think about like making these hand gestures and make mountains and valleys. The local, there's just a lot more to it. That seem okay? All right. So I think we, homework 216, and we can cut that off. Tomorrow would be a book homework talk sort of day. I gave you a sheet. The sheet would be due in 2 days. If you need a second sheet, we could do a second sheet. But we'll come up on a quiz just on 4.1 and 2. 4.1 is hard. This isn't really nearly as hard. You just need to keep straight what the system is for each. That's the big thing is at first, just straightening out, like, use the original for yes, use the derivative for that, like what's what are the rules. But once you get the systems straightened out, this isn't bad. But I don't want to keep building. We want to review some 4.1 stuff, review this stuff. We'll take a quiz before we go popping up to 4.3.